Evaluation indices, three three indices including the peak signal to noise ratio, structural similarity index measure SSIM, and the spectral angle mapper are chosen to evaluate the reconstructed result in this article. PSNR is used to depict the error between corresponding pixels. SSM defines the structural information and reflects the structure of objects in the images. SAM is calculated on each spectral vector and the average overall spatial thickness. We use the mean BSNR. Mean BSNR is the MPSNR, values of all bands. The mean of SSM, MSSIM, values of all bands and SAM to objectively evaluate the reconstructed results of simulated experiments. The larger MPSNR value, the larger MSSA value, and the smaller SAM value mean better reconstructed result. Once again, the larger MPSNR value, the larger MISSM value, and the smaller SAM value mean a better reconstructed result. Here data sets remotely sensitive HSI are selected, that is Pavia Center and Pavia University. Second one, the CAVE dataset comes from Computer Vision Association and it contains 32 images. Third one, Harvard dataset records 50 images. Fourth one, ICVL dataset currently records 201 images from 400 to 1000 nanometer with an increment of 1.25 nanometer. Results on HSI datasets. Table 1 reports the reconstructed results, different methods HSI datasets. The best reconstructed results are highlighted in bold. The second results are underlined. We can observe that the GNLR method has obvious advantages in MPSNR, MSSIM, and the SAM values. For example, the proposed method achieves around 4 dB improvement of the MPSNR value compared to the second best method on the toy image. Figure 3 shows the PSNR values of each band on 4 HSI datasets. It can be observed that the proposed method gains the best performance over the competing methods. Furthermore, since DSA ignores the spectral correlation and the low rank matrix based NG-meet cannot fully characterize the global structure of the tensor, the same value of the GNLR method gains the best performance, which indicate 3TTNN can preserve the global structure. Figure 4 and 5 plot the spectrum profiles Pavia Center and Pavia University. Already we have seen the figure 4 and 5. We can observe that the reconstructed spectrum curves of the proposed method close to the original curves, which further verifies the GNLR well preserves the spectral information in most bands. In figure 6 to 10, show the reconstructed images and fonts color CAP TV, TSA, NG-meet, and GNLR methods. As the observed reconstructed images, GNLR can provide more details and structure than competing methods. More specifically, from figure 6, we notice that the reconstructed images of CAP TV and DSA methods are too blurred to distinguish the gap between the region through the enlarged boxes and the NG-meet method contributes to the improvement of the whole structure, but some details are lost. So in discussion, influence of different periods, we illustrate the influence different periods proposed model, reconstructions including global role, randomness, non-local, sparsity, non-local, low randomness, WNM. Figure 11 shows the false color images reconstructed results by different Fourier star imaging when the only TNN 3TNN, WNM or PM3D performed, we can observe that the structure is reconstructed with extra details lost. When two periods of them are used simultaneously, both the details preservation and index evaluation are better than using one period. See figure 11G. From figure 11H we can observe that the proposed GNLR which integrates three periods achieve the closest visual effect to the original image and the best evaluation result. Figure 12 shows the spectrum profiles between the original reconstructed results by different periods compared with 1D. So we already seen the figures 6. And then effects of bad number, parameter discussion, where we have discussed it, and then penalty parameters. Regularization parameters, lambda, I, we have seen already. In this conclusion, here, in this article, we have suggested a low rank tensor optimization method with non-local PnP relationship to reconstruct the HSIs from 2D measurements in SEA systems, which simultaneously explores the global low rankness, non-local sparsity, and the non-local low rankness. The proposed model, the 3D TNN, is employed to preserve the global correlation of the underlying HSA along with the three directions and two implicit regularizations under the PnP framework are used to flexibility capture the non-local similarity of the coefficient tensor, which leads to lower computational complexity. Specifically, the two regularizations, that is PM3D and WNM denoises, characterize interpatch and interpatch redundancy similar 2D batches and interpatch redundancy similar 3D batches respectively. All regularization stems in the proposed model are complementary to boost reconstruction performance. Extensive experiments on HSI datasets demonstrate superiority of our method over compared state of the other odds. In this paper, they have used tensor-based degradation model, proposed GNLR model, and algorithm, ADMM algorithm for solving GNLR problem. And then results, output of this paper. This is for algorithms and mathematical operator. Here, this is for result out of the paper. Here, here in global results, global low rank tension optimization model with non-local plug and play PnP regularizers GNLR method has obviously advantages in mean PSNR, mean PSNR, MPSNR. Mean structural similarity index measure, that is MSSIM, and the spectral angle mapper, that is same values. The proposed method achieves around 4 dB improvement of the MPSNR value. When mu equal to 10 to 5, MPSNR value 29.283 dB. When mu equal to 0.1, PSNR value 29.285. The larger the proposed method, see, the larger MPSNR value, the larger MISSIM value, and the smaller SAM value mean a better reconstruction result here. And then here, actually, achievement in the research work here, to boost the reconstruction performance is the achievement of the research. In another goal also, research goal also in this paper, low computational complexity. Low computational complexity is the important point. Once again, we will see the figure again. Illustration of global and non-local periods of the proposal GNLR model. Top, the clean HSI. Bottom, the coefficient tensor. Here, in A, first one, original image. Top, clean HSI. Bottom, coefficient tensor. Here, original image. Global period. N1, N2, N3, global period. Here, in second, R, N2, N1, coefficient tensor, x in t, x3, e power t, non-local period. B, this is B, top, the global low rangeness of the HSI, the global low rangeness of the HSI, middle, top the global low rangeness here, singular value in y-axis, x-axis minimum n1, n2, slice 2 to n, n2 like this. Here in middle, non-local transformed sparsity. Here, interpath redundancy, intrapath redundancy, stack here 20 patches, number of pixels, pixel value in x-axis. Middle, non-local sparsity of the coefficient tensor. Bottom, the non-local low rangeness of the coefficient tensor. Bottom, the non-local low rangeness of the coefficient tensor. Reshape, non-local low rangeness, intra-batch redundancy, reshape 3D batches, P square R, D, singular value, index 0 to 300, 0 to 1, 0 to 6, singular value, and then reconstructed results of 3TNN, GNLR and NGMeet. This one 3TNN reconstructed images, MPSNR 27.26 dB. In GNLR, MSPNR equal to 29.33 dB. In NGMeet, MPSNR 27.21 dB. So here is the GNLR is the highest one. And here the another one figure, A illustration of SCI process